At the end of this video, you should be able to distinguish between torque and force, calculate the magnitude of a torque on an object, identify the 6 types of simple machines, and calculate the mechanical advantage of a simple machine. Chapter 7, Section 4, Torque and Simple Machines. Rotational motion. Earlier, you studied various examples of uniform circular motion, such as the spinning Ferris wheel or an orbiting satellite. During uniform circular motion, an object moves in a circular path and at constant speed. An object that is in circular motion is accelerating because the direction of the object's velocity is constantly changing. This centripetal acceleration is directed toward the center of the circle. The net force causing the acceleration is a centripetal force, which is also directed toward the center of the circle. In this section, we will examine a related type of motion, the motion of a rotating, rigid object. For example, consider a football that is spinning as it flies through the air. If gravity is the only force acting on the football spins around a point called its center of mass. As the football moves through the air, its center of mass follows a parabolic path. Note that the center of mass is not always at the center of the object. Rotational and translational motion can be separated. Imagine that you roll a strike while bowling. When the bowling ball strikes the pins spin in the air as they fly backward. Thus, as they both have rotational and linear motion. These types of motion can be analyzed separately. In this section, we will isolate rotational motion. In particular, we will explore how to measure the ability of a force to rotate an object. The magnitude of a torque. Imagine a cat trying to leave a house by pushing perpendicularly on a cat flap door. Figure 4.2 of your text shows a cat flap door hinged at the top. In this configuration, the door is free to rotate around a line that passes through the hinge. This door's axis of rotation. When the cat pushes the bottom edge of the door with a force that is perpendicular to the door opens. The ability of a force to rotate an object around some axis is measured by a quantity called torque. Torque depends on the force and the lever arm. If a cat pushed the door with the same force, but at a point closer to the hinge, the door would be more difficult to rotate. How easily an object rotates depends not only on how much force is applied, but also on where the force is applied. The farther the force is from the axis of rotation, the easier it is to rotate the object and the more torque is produced. The perpendicular distance from the axis of rotation to a line drawn along the direction of the force is called the lever arm. Figure 4.3 on the screen here shows a diagram of the force F applied by the cat perpendicular to the cat flap door. If you examine the definition of lever arm, you will see that in this case, the lever arm is the distance D shown in the figure, the distance from the pet's nose to the hinge. That is, D is the perpendicular distance from the axis of rotation to the line along which the applied force acts. If the cat pressed on the door at a higher point, the lever arm would have been shorter. As a result, the cat would need to exert a greater force to apply the same torque.
Torque is a quantity that measures the ability of a force to rotate an object around an axis. When you use a wrench to loosen a bolt, the magnitude of the torque on the bolt depends on the magnitude of the applied force and the length of the lever arm. The length of the lever arm is determined by the angle theta. The lever arm is the shortest distance from the axis of rotation to a line drawn along the direction of the force. For a given force, a longer lever arm produces a greater amount of torque.
The lever arm depends on the angle. Forces do not have to be perpendicular to an object to cause the object to rotate. Imagine the cat flap door again. In figure 4.4a on the screen here, the force exerted by the cat is perpendicular to D. When the angle is less than 90 degrees, as in B and C, the door will still rotate, but not as easily. The symbol for torque is the Greek letter tau, kind of like a one-legged pie. And the magnitude of the torque is given by the following equation. Torque is equal to force times distance times the sine of theta, which is to say torque is equal to force times the lever arm. The SI unit of torque is the Newton meter. Notice that the inclusion of the factor sine in this equation takes into account the changes in torque that are shown in figure 4.4. Figure 4.5 of your text shows a wrench pivoted around a bolt. In this case, the applied force acts at the angle to the wrench. The quantity d is the distance from the axis of rotation to the point where the force is applied. The quantity d sine theta, however, is the perpendicular distance from the axis of rotation to a line drawn along the direction of the force. Thus, d sine theta is the lever arm. Note that the perpendicular force between the door hinge and the point of the application of force F in figure 4.4 decreases as the cat goes further through the door. The sign of a torque. Torque, like displacement and force, is a vector quantity. In this course, we will assign each torque a positive or negative sign, depending on the direction the force tends to rotate an object. We will use the convention that the sign of the torque resulting from a force is positive if the rotation is counterclockwise, and negative if the rotation is clockwise. In calculations, remember to assign positive and negative values to forces and displacements according to the sign convention established in the chapter Motion in One Dimension. For example, imagine that you are pulling a wishbone with a perpendicular force F1 and that a friend is pulling in the opposite direction with a force F2. If you pull the wishbone so that it would rotate counterclockwise, then you exert a positive torque of magnitude F1d1. Your friend, on the other hand, exerts a negative torque, negative F2d2. To find the net torque acting on the wishbone, simply add up the individual torques. Net torque is equal to the sum of torques, which is equal to torque 1 plus torque 2, which is equal to F1d1 plus negative F2d2. When you properly apply the sign convention, the sign of the net torque will tell you which way the object will rotate, if at all. At this point, you should be able to understand sample problem E.
Torque, like displacement and force, is a vector quantity. It has both magnitude and direction. However, if we assign a positive or a negative sign to the quantity of a torque to indicate its direction, we can treat torque as a scalar. The convention we will use is that the sign of the torque is positive if the applied force tends to cause a counterclockwise rotation. If the applied force rotates the object in the clockwise direction, the torque is negative.
Types of simple machines. What do you do when you need to pry a cap off a bottle of soda? You probably use a bottle opener. Similarly, you would probably use scissors to cut paper or a hammer to drive a nail into a board. All of these devices make your task easier. These devices are all examples of machines. The term machine may bring to mind intricate systems with multicolored wires and a complex gear and pulley system. Compared with internal combustion engines and airplanes, simple devices such as hammers, scissors, and bottle openers may not seem like machines, but they are. A machine is any device that transmits or modifies force, usually by changing the force applied to an object. All machines are combinations or modifications of the 6 fundamental types of machines, called simple machines. These 6 simple machines are the lever, pulley, inclined plane, wheel and axle, wedge, and screw.
A simple machine changes the direction or amount of a force. Simple machines include levers, wheels, pulleys, inclined planes, wedges, and screws.
Using simple machines. Because the purpose of a simple machine is to change the direction or magnitude of an input force, a useful way of characterizing a simple machine is to compare how large the output force is relative to the input force. This ratio is called the machine's mechanical advantage. It is written as follows: MA is equal to F sub out divided by F sub in, which is to say mechanical advantage is equal to output force divided by input force, which is also equal to perpendicular distance in divided by perpendicular distance out. One example of mechanical advantage that is commonly used is the use of a back of a hammer to pry a nail from a board. In this example, a hammer is a type of lever. A person applies an input force to one end of the handle. The handle, in turn, exerts an output force on the head of the nail stuck in the board. If friction is disregarded, the input torque will equal the output torque. This relation can be written as follows: torque in is equal to torque out. Also, force input force, multiplied by perpendicular distance in is equal to output force multiplied by perpendicular distance out. Knowing our definition of mechanical advantage, substituting this expression into the definition of mechanical advantage gives us the following result. Mechanical advantage is equal to F sub out over F sub in, but also equal to perpendicular distance in divided by perpendicular distance out. The longer the input lever arm as compared with the output lever arm, the greater the mechanical advantage is. This in turn indicates the factor by which the input force is amplified. If the force of the board on the nail is 99 newtons, and if the mechanical advantage is 10, then an input force of 10 newtons is enough to pull out the nail. Without a machine, the nail could not be removed unless the input force was greater than 99 newtons. Machines can alter the force and the distance moved. You have learned that mechanical energy is conserved in the absence of friction. This law holds for machines as well. A machine can increase or decrease the force acting on an object at the expense or gain of the distance moved. But the product of the two, the work done on the object, is constant. For example, figure 4.8 on the screen here shows two examples of a trunk being loaded onto a truck. Figure 4.9 illustrates both examples schematically. In one example, the trunk is lifted directly onto the truck. In the other example, the trunk is pushed up an incline into the truck. In the first example, the force, F1, of 360 newtons is required to lift the trunk, which moves through a distance, d1, of 1.0 meters. This requires 360 newton meters of work, which is to say 360 newtons multiplied by 1 meter. In the second example, a lesser force, F2, of only 120 newtons would be needed, as long as we ignore force, but the trunk must be pushed a greater distance, d2, which is 3.0 meters. This also requires 360 newton meters of work, which is 120 newtons multiplied by 3 meters. As a result, the two methods require the same amount of energy. Efficiency is a measure of how well a machine works. The simple machines we have considered so far are ideal, frictionless machines. Real machines, however, are not frictionless. They dissipate energy. When the parts of a machine move and contact other objects, some of the input energy is dissipated as sound or heat. The efficiency of a machine is the ratio of useful work output to work input. It is defined by the following equation. Efficiency is equal to output work divided by input work. If a machine is frictionless, the mechanical energy is conserved. This means that the work done on the machine, input work, is equal to the work done by the machine, output work, because work is a measure of energy transfer. Thus, the mechanical efficiency of an ideal machine is 1, or 100%. This is the best efficiency a machine can have. Because all real machines have at least a little friction, the efficiency of real machines is always less than 1.
The mechanical efficiency of a machine compares the amount of work energy output by the machine to the amount of work energy input into the machine. In the case shown here, energy is put into the system by the force that moves the block up the incline. As a result, the block gains gravitational potential energy. This is the output work of the machine. Mechanical efficiency can be calculated using the equation shown here, where W out is the energy gained by the object and W in is the energy put into the system. In a frictionless system, the energy gained by the object would be equal to the energy put into the system, and the efficiency would be equal to 1. In real-world machines, however, there is always energy lost to friction, so the efficiency is always less than 1.
At this point, you should be able to distinguish between torque and force, calculate the magnitude of a torque on an object, identify 6 types of simple machines, and calculate the mechanical advantage of a simple machine.